Let's start with the model we created in the tutorial Modeling Contact Pairs method. The model was complete and working perfectly, so we will only make the necessary changes from the Contact Pairs method to General Contact and leave the rest of the model as it is. Expand the Interaction Properties container. We see the two interaction properties defined in the previous tutorial. Frictional specifies a tangential behavior with a penalty friction formulation, isotropic directionality, and a friction coefficient of 0.1. Frictionless, as the name implies, specifies a frictionless friction formulation as its tangential behavior. Expand the interactions container. We see the two contact pair interactions we specified as part of the simulation in the previous tutorial. Since we will be using general contact, we do not need to specify contact pairs. Let's delete both of these by right-clicking on them and choosing Delete. Double-click Interactions. In the Create Interaction dialog box, you don't initially see General Contact as an option. This is because you are in the Make Contact step. In Abaqus Standard, General Contact can be defined only in the initial step, and it will remain active in all subsequent steps. In Abaqus Explicit, on the other hand, General Contact can be defined in any step. Since we are using static general steps in this analysis, we must define General Contact in the initial step in keeping with the Abaqus Standard requirement. Change the step to Initial. Abaqus now lets you specify General Contact as the procedure. Name the interaction Contact Between Parts. In the Edit Interaction dialog box, set the contact domain to All with Self. This tells Abaqus to automatically detect contact, including self-contact between faces of parts. Note that analytical rigid surfaces, shell edges, beam segments, and reference points are excluded by the general contact algorithm. You can also choose to exclude individual surface pairs by clicking the Edit button labeled Excluded Surface Pairs. The other contact domain option, Selected Surface Pairs, allows you to specify individual contact surface pairs similar to the Contact Pairs method. Now let's assign attributes to the contact interactions. In the Contact Properties tab, set Global Property Assignment to the interaction property called Frictionless that we defined earlier. This will set all contact interactions detected by Abaqus during the simulation to use this property. We wish to specify a different interaction property for contact between the curved block and the bottom of the plank. We can override the global property assignment by setting individual property assignments. Click the Edit button next to Individual Property Assignments. In the Edit Individual Contact Property Assignments window, choose Curved Block Top, Rect Block Bottom, and Frictional as the contact pairs and contact property. If Highlight Selected Regions is checked, Abaqus will highlight the chosen surfaces in the viewport. Then click the arrows to move your selection into the table listing the contact domain. Note that the order of the surface pairing is irrelevant. Also, if you wish to specify self-contact, you would select either the same surface or self in the second column. Click OK to accept. As discussed in the Contact Pairs tutorial, contact initializations determine how Abaqus adjusts surfaces before the analysis. This includes strain-free adjustments to make surfaces touch exactly at the beginning of the analysis, or treating contact interactions as interference fits. We will not use any contact initializations. Switch to the Surface Properties tab. Here you can specify non-default surface properties to use for surfaces involved in general contact interactions. These properties are not considered when the surfaces are involved in other interactions. They are only used for general contact interactions. Surface properties for general contact are assigned at the beginning of the analysis and cannot be modified across steps. Surface thickness assignments allow you to specify a value for the surface thickness or a thickness scaling factor. This surface thickness will not affect the structural properties. However, it may be used to achieve the effect of a finite thickness surface coating when establishing contact. Shell membrane offset assignments allow you to specify an offset distance between the actual midplane of a thin body and its reference plane, which is the set of nodes and elements that define the surface feature in Abaqus. Surface offsets can only be specified for surfaces defined using shell elements and similar ones such as membrane elements. By default, the surface offsets that you specify in the section definition that is assigned to the part will be used by the general contact algorithm. However, any surface offsets you specify for general contact will not change the element integration. We will not specify any shell offsets in this demonstration. Surface smoothing was discussed in the contact pairs tutorial. Curved geometric surfaces tend to be approximated as a faceted group of connected element faces rather than their true geometry, which can cause inaccuracy in contact interactions. Surface smoothing overcomes these difficulties by more closely approximating the smooth surface behavior with continuous normals during an analysis. Surface smoothing is active by default in general contact. We will disable it. Click the Edit button next to Surface Smoothing Assignments. Uncheck Automatically Assign Smoothing for Geometric Faces. Click OK. Switch to the Contact Formulation tab. The general contact algorithm in Abaqus Standard enforces contact in an average sense between the interacting surfaces. Master and slave surfaces are automatically assigned by Abaqus Standard. If, however, you wish to define the master and slave role for specific contact pairs, you can do it here by clicking the Edit button next to Master-Slave Assignments. The interaction property specified will override the global properties for that contact pair, as the general contact algorithm automatically avoids processing interactions that are treated by the contact pair algorithm. We shall not make any master-slave assignments in this example. Click OK to close the Edit Interaction dialog box. We've now removed the contact pair interactions and replaced them with the general contact formulation. Since the rest of the model setup is already complete, we are ready to run the job. Double-click on the Jobs container to create a new job called General Contact Simulation Job. Run the analysis. Once the analysis is complete, view the results. You see that Abaqus has correctly determined the contact interaction between the rectangular block and the top of the plank using the general contact algorithm, even though this contact pair was not specifically identified by us. It has used the global frictionless interaction property. The interaction between the plank and the curve block, which was identified using master-slave assignments, is also handled correctly by Abaqus. We already explored how to view the contact pressures in the previous tutorial. This was done using the cpress variable and using the frame selector. Another nodal field output variable that is written to the output database for contact problems is the frictional shear stress, for which you have C shear 1 and C shear 2 that are perpendicular to each other. Select C shear 2. You see that shear forces are generated in the interaction between the curved block and the plank where friction was specified. These frictional shear stresses are not seen between the rectangular block and the plank, which had a frictionless interaction. To make sure, you can hide the plank in the curved block. No shear stresses are present at the interface between the rectangular block and the plank. There are many history output variables that can be requested for contact simulations. We have not used these in this example, but for future reference, you can find them in the History Output Requests in the Model Setup. Switch back to the Model tab. Double-click HOutput1 in the History Output Request container. Under Contact, you see a number of variables you might find useful for your contact simulations. And that concludes this tutorial.